Scene 1, The Discrepancy Revealed. Welcome to the 10th lecture of our wave mechanics series. Today, we address a fascinating and profound question: why doesn't the microwave absorption peak occur exactly at a 180-degree phase difference between the front reflection R1 and the rear reflection R2? According to naive intuition, perfect cancellation should happen when R1 and R2 are exactly out of phase at 180 degrees. Yet, rigorous experimental data and exact transmission line equations reveal a consistent shift. The absolute minimum of reflection loss, absolute RL, actually occurs at a phase difference greater than 180 degrees. Meanwhile, the maximum amplitude of R2 is shifted to a phase difference less than 180 degrees. For half a century, mainstream theories like the quarter wavelength model could not offer a clear or physically consistent explanation for these shifts. Our wave mechanics theory solves this puzzle elegantly using basic wave superposition principles. Scene 2, The Interference Attenuation Balance. To understand this shift, let us perform a simple mental experiment. Imagine if the amplitude of the rear interface reflection R2 were a constant, independent of the phase difference. In this idealized case, the reflection loss would be governed solely by the phase effect. The rate of change of RL with respect to phase difference would be exactly 0 at 180 degrees, meaning the absorption peak would align perfectly with the 180-degree line. But in any real absorbing film, R2 is not constant. As the film thickness d increases, the phase difference increases, but simultaneously, the material's attenuation dampens the amplitude of R2 at a constant, monotonic rate. Let us look at what happens at exactly 180 degrees. Because the phase difference is 180 degrees, the phase effect is at its extreme. But since the amplitude of R2 is still decreasing as thickness increases, this amplitude decay continues to drive the combined reflection loss, absolute RL, even lower. Therefore, the absolute minimum of RL is dragged past 180 degrees. Only when the phase effect, which wants to increase R2 as the phase difference shifts toward 360 degrees, perfectly balances the monotonic material attenuation effect, does RL reach its true minimum. This balance occurs at a phase difference greater than 180 degrees. Once the phase effect dominates, RL begins to rise. Scene 3, The Compelling Evidence and Scientific Comparison. Our wave mechanics theory explains this shift using nothing more than undergraduate wave superposition and simple derivatives. It is an unassailable proof of the theory's correctness. Contrast this with mainstream impedance matching and quarter wavelength models. Mainstream authors have long recognized that absorption peaks deviate from the quarter wavelength thickness. To explain this, they published papers with highly complicated, dense, and difficult to follow mathematical treatments. But as we proved in our critiques published in Materials Chemistry and Physics and Journal of Applied Physics, these complex formulations are mathematically and physically flawed. They run in circles because they fail to grasp the fundamental nature of wave cancellation. The truth is often incredibly simple. De Dao Ji Jian, the greatest truths are the simplest. Flawed theories appear complex and mature, but in reality, their complexity is merely a symptom of missing the physical core. When you grasp the essence, a complicated problem can be solved with middle school math and undergraduate physics. Scene 4, The Systemic Crisis in Academic Publishing. This brings us to a troubling reality in contemporary scientific publishing. Why does modern academia favor complex, flawed models over simple, correct ones? If you write a paper full of incorrect formulas that fit experimental curves, it gets published and heavily cited. But if you expose these errors and present a simple, correct wave mechanics alternative, mainstream journals often reject it as too simple or low-level. This intellectual decline has turned academic publishing into an autocracy of peer-reviewed censorship. Scientists continue to cite flawed, unphysical papers because their own work is built on those very same errors. If your foundation is wrong, can your conclusions ever be right? We must have the courage to demand logical consistency and physical correctness. We must reclaim scientific publishing as a pursuit of true knowledge, not a cargo cult of empirical curve fitting. Explore our complete series of proofs on Substack, SSRN, and ResearchGate. Thank you for your commitment to scientific truth.